super quick?
Yeah, it goes directly to YouTube, which is perfect because we don't have to like save it to our computer, then upload it. All these servers are just that's probably in the same server, even the same data center. It just stays there. But yeah, it's really convenient.
Good answer? Yep.
Awesome. All right. Again, sorry for the delay, anybody who's watching this live on YouTube and those in the Zoom call, but we'll get started. Welcome everybody to this HackFS workshop. Today we have Alan and David. They're with the Protocol Labs team. They work on some specific things within that part of the ecosystem, and they'll talk about that before I pass, or just after I pass it over to them. But before that happens, let's see if there's any logistics for HackFS. Today is Wednesday, midweek in week 2. Everybody should have had their check-ins, their first check-ins already. You've been putting cohort channels in the Slack. If you aren't familiar with what that is, or you were surprised to find yet another channel, that's the way we keep track of teams and projects that they're working on. So we have a way to track chunks of hackers and their teams and the progress that people have been making throughout the week. So that's what cohorts are for. If you haven't already, go to your Hacker dashboard, and that's where you'll actually be inputting your weekly check-ins, and then that ends up in our back end. So make sure you're putting it in both places, both your cohort channel and your Hacker dashboard. We have a couple more events. There's, I think, 2 office hours tomorrow with some of the sponsor teams. I would check that out in the HackFS schedule channel. And you probably all have received several calendar invites. So if you haven't, check your spam. Maybe it's going there. Hopefully not. I think that's about it. All the logistics stuff I had to cover for HackFS. It's been great. This week is a little bit more relaxed than week 0 and week 1. So I know Andrew and I are happy, but we're glad to be continuing to provide workshops and running these sessions for everybody. And we can turn it over to Alan and David. Do you want to give an intro to yourself and what you're going to be talking about?
Of course. Thank you so much. Hi, everyone. Really excited to be here. If you are looking for some randomness, you are in the right place. Welcome to the DRAN workshop, where you will learn how to harness the power of true unbiasable randomness for great good and fun with friends. So my name is David, or David, whatever you prefer. I'm a research engineer at Protocol Labs, working on the research group Resilient Networks Lab, ResNet Lab for short. I've been with Protocol Labs for 5 years now, and when I joined to work specifically on the IPFS project and the Lead peer-to-peer project that you might have heard about or maybe even used. 12 weeks ago, I joined this new project, the DRAN project, to take it from a research experiment to a production service, and you will learn more about it. Alan, do you want to give us a quick introduction about yourself as well?
Sure thing. I've been working for Protocol Labs for around, I guess, 3 years now. Before that, I had my own business with my friend, and we were building crazy things for entrepreneurs that had little amounts of money, but also organizing like events and meetups and things in London, UK, IoT stuff and other application things. But yeah, when I joined Protocol Labs, I was mainly in like the web and GUI team, and then I kind of transitioned to doing JS IPFS and leading that for a while, and now I'm just guns for hire on whatever project, and now I'm working on DRAN with David. So that's me.
All right, thank you. So yeah, like DRAN is a distributed randomness beacon that offers you verifiable and predictable and unbiased random numbers as the service. So it's kind of like unique in its kind, but like before like really going into the details of DRAN, like start off with a quick motivation and like understand why randomness is important. And so randomness has a ton of use cases in our kind of like all kinds of applications that we use and all kinds of like businesses that we rely on. Things from lotteries, election event audits, controlled trials, even in the protocols that we use, from like the ability to choose random peers for our gossiping protocols, the ability to have random numbers that can get used for cryptographic protocols, and much more. However, despite this being such like a useful thing and a used thing, the reality is that historically having pure and secure randomness is incredibly hard. And the fact that we have used less than secure randomness in the past has led to many attacks, many scams that like were able to be possible just because the randomness was not secure, that like led to either stealing money or even just like taking services down. Additionally, well, we are in a HackFS, the Ethereum, IPFS, and Filecoin hackathon. You might know that like randomness is really critical for blockchains. And so all kinds of cryptographic protocols used in blockchains, from proof of stake, replication, retrievability, verifiable computation, proof of stake, require randomness. And despite it being such a requirement, there still isn't a one-size-fits-all solution for randomness that is also unbiasable and available. Most protocols, most proof-of-stake protocols attempt to solve it, but at a big cost by adding a lot of complexity and brittleness to the protocol. And often the way that it gets done, it gets so integrated with a lottery use case on the blockchain itself that it's not really usable by the applications that are riding on top. Most of the solutions that exist today like took years to produce, but they still are, they still have yet to stand the test of time. So they haven't been battle tested enough. And like the randomness that gets used in these protocols is for the random leader election, which is a hard problem. You might be familiar with some solutions that get used in different blockchains, from proof of work, which is probably the most widely used one. But like, as we know, it's extremely expensive computationally and financially, and also the economies of scale typically force like some degree of centralization on the network. Then there's on-chain randomness that gets often used for proof of stake protocols. However, from what we can gather, like most of the variations out there are actually still biasable by agents such as miners. So they are not 100% secure. One thing that is very promising is verified delay functions. And so a verified delay function is just a function that executes for a period of time, and that you are able to prove that the function executed for that period of time, not more, not less. That is going to be very useful because we can combine that with a zero, like a ZK snark, a circuit in which we can have something that is completely a black box, opaque, that generates randomness at every epoch that everyone can verify. However, the theory is being developed right now. The research is being developed. There is nothing that exists in practice, despite a lot of R&D. And we believe like it's coming, but it's still possibly like 2 to 5 years away, if not more. And the reason why this, like, because this problem is so hard, and because existing solutions are either brittle or expensive or not ready yet, there is a reason why protocols such as Ethereum 2 and Filecoin are moving to separate chains to get their randomness sources. And so in addition to that, we actually believe, Berkeley Labs and the Drand team, that we, as internet users, as internet builders, we need a randomness service in the same way that we have a name service like DNS, same way that we have a time service like NPTP, PKI, and certificate transparency. We also need to offer a core service of the internet that offers a secure randomness source. And so this is where we actually enter Drand, because Drand is an unbiasable randomness beacon that is tested, audited, and ready to use. So how does Drand work, the simplified version? There's a lot of like dark magic happening underneath the hood, but like the simplified version is a Drand network is composed by 2 or more Drand nodes. And ideally, these nodes are independent. And then the network itself is assembled in 2 parts or phases. There is the setup phase, where there is a distributed key generation ceremony. This is where, before even generating any randomness, nodes get together and they agree on a threshold parameter. So the threshold parameter is the number of nodes that need to be online in order to generate randomness. So imagine like the network of 10, if you set up the threshold 7, then as long as 7 nodes are up, you can generate randomness. And then you also agree on the period, like the epoch. So if you are going to generate a randomness value at every 30 seconds, at every 25, at every minute. And so once they agree on these values, they generate their own key material and they create their signature so that they can verify other nodes' signatures and complete the distributed key generation phase. Then it goes into the second phase, and this is the final phase, where randomness can be generated forever. And so in a randomness generation phase, we basically at every epoch, every node will generate a partial signature using their key material. And once there is a threshold of nodes that collects enough partial signatures from other nodes, they can smash them together and create a single signature that then gets broadcasted to the world. And it's where with that single signature that nodes will verify that it was indeed generated by the partners from the network. So it's verifiable, and verify and we'll get the randomness by hashing the signature. So the randomness will be the hash of this signature. And this is just a typical BLS signature that you might have heard about. If you want to understand like the guts and the math like that happen inside DRAN, the dark magic, there's a very interesting talk on Protocol Labs research website. You also have the link here down below, where Nicholas, the author of DRAN, actually goes into the detail of how this works. So if you are into that, just definitely check it out. With this construction, what we get is a network that is decentralized, where like the nodes are operated by different entities, and there is no central point of failure because one node can fail. As long as we have a threshold of nodes, the network can continue to operate. It's unpredictable because the randomness is like multiple partial signatures coalesced together. So only when you have all these partial signatures, you actually can see the value. So no node can actually predict what is the next value because it will need to collude with the other nodes. And it's unbiasable. So even if there is a node that is malicious and can attack the other nodes to get their key material, there is no way that the randomness would change. What they could do in that scenario would be just like to predict the future. But in that case, there is a way to do a resharing session where the key material gets rotated. And then it's verifiable. Like clients can verify that the randomness came from exactly the network that they trust, that was generated at the precise moment that they wanted, and they therefore can use it for their application. If you are interested on understanding how this works underneath and what is the threat model, we actually have all this information available right now in our beta website, where you can understand what is the threat model and why we are able to make the claim that these properties are there. Well, this is Drand, the protocol and the project. But then there is Drand, the network, and you might have heard about the League of Entropy. So the League of Entropy is the first incarnation of a DRAN network that is operated by these multiple partners. And this, the League of Entropy had an amazing launch with companies like Cloudflare, Kudelski Security, C40T, EPFL, University of Chile, and Protocol Labs joining to have a network that can then generate randomness that could be used by other projects. And apparently my screenshot is still loading. Thanks, Google Slides. But no worries, you'll see it on Alan's part. I was just like showing fresh randomness there. The next point is really the network keeps growing. So the network becomes more and more secure as more partners join. And so we went from the previous partners I already talked about to include UCL, ChainSafe, Truffle, Emerald, Onion, Ethereum, PTSP, Cello, and many more are joining as we speak. And additionally, now that this network is moving from a research experiment to a production service, we actually are getting the first production user, which you might have heard about it. It's called Filecoin. So Filecoin is going to be the first production user of the Drand protocol and the League of Entropy service. And Filecoin decided to do that so that like, it has a secure and unbiasable randomness source for the random leader election problem that exists, or the random leader election challenge that exists inside the Filecoin protocol. And so we have been getting the Drand project ready for this big user and for this big launch. And so we have been working to get the version 1.0 ready. And I'm really happy to share with you all that it has been launched this month, actually last week. So when you install Drand, you're already using the latest version 1.0. And what got included with version 1.0 is that we upgraded the network from a single layer to a 3-layer. So now we have 3 layers where the first one is just the Drand nodes connecting to other Drand nodes, and they are protected. There is no one from outside the internet that can connect to them. And this is where the randomness gets generated. Once the randomness is generated, it gets pushed to the distribution layer. And the distribution layer are multiple CDNs like Cloudflare CDN, CloudFront, and even Leap peer-to-peer pubsub relays, so that we have multiple transports to get the randomness to clients depending on their geographic location and network conditions and so on. And additionally, there is the client network, which in addition to just acting as clients, pulling the randomness from the network, they can also help each other by being pubsub relays. And so a client can also share the randomness, broadcast the randomness to other nodes. We deployed a network observatory. So this is a way for us to measure the quality of service that Drand is offering to the network. And we have multiple probes all over the world that are always taking samples and measuring what is the latency from randomness being generated to randomness being received. And one thing that we are really happy about is that we managed to get a 400 millisecond delivery boost to the nodes in China, thanks to the Leap peer-to-peer pubsub relays. So we managed to get a 400 millisecond speed boost in comparison to the popular CDNs. We also have network monitoring. So we are now monitoring all the nodes, and there's a status page that you can check to see how live the network is. There is a new documentation website. Right now it's available on beta.drand.love. We are sharing with this group, with the HackFS group. We haven't launched it to the world yet, so please just know that when you tweet about it. And what you can expect is that there will be a League of Entropy mainnet upgrade coming really soon. And so this upgrade, just to be very clear, is that there has been a League of Entropy mainnet running for more than a year. Now we launched the League of Entropy testnet to test all of these latest features, and we are going to do the actual launch of the upgrade very, very soon. Nevertheless, don't despair. You can actually use the League of Entropy testnet just fine. It's literally a replica of the mainnet anyway, so you can use the testnet to build your applications while you are in the HackFS hackathon. So now, with all of this, let's get into the meat of this workshop, which is actually the fun demos and hands-on material that Alan is going to walk us through. Thank you, and I don't see questions so far. Go ahead, Alan.
Cool, thank you, David. Okay, so are you ready?
Yes.
Okay, you all look ready, I'm sure. Okay, now you know a little bit about what Drand is. We're going to use the Go and JS clients to get hold of some of that box fresh random goodness from the Drand nodes that the League of Entropy run. And so today, what we're going to do is mostly get randomness from the JSON HTTP API, but we're also going to try and get a live feed of randomness using libp2p pubsub if we have time at the end. So this is a workshop, so you can try and code along with me. There's a lot to cover, so I'll go reasonably fast, but don't worry if you get lost or can't follow quick enough. It's fine to just watch and take it in. I will publish or give the walkthrough, the recipe that I'm using for all of the work that we're doing at the end of the workshop. So you are welcome to just watch, that's fine too. All right, so let's get on with it. Let's get some information about the chain of randomness, and we'll use the Go client for this. And so just to explain about the chain of randomness, Drand produces this chain of randomness, and each new beacon points back to the previous beacon. So when I talk about getting hold of the chain information, the kind of information that's useful to us is the period between beacons. So every so often, randomness beacons are generated and emitted. And so knowing the time between them is useful. Also the genesis time, the time that the chain actually started. And with the period and the genesis, we can then say, well, the next randomness beacon is expected to be generated at this point in time. So that's useful too. And then the public key is interesting chain information, because that actually allows us to verify that the randomness beacons that we get hold of are valid and good. All right, let's get going. I'm going to share my screen now. So hopefully this will do good. You should see the DRAND website here. So this is, like David said, it's at beta.drand.love at the moment. It will be available at drand.love soon. If you head on over to the developer section, you will see there are documentation for the 2 client libraries that we're going to be using today. And also for there's just the HTTP API. It's super simple. There's only 3 endpoints. But there's documentation for that as well. But we're going to use the client libraries today to get hold of that randomness, which is going to be fun. So let's start. Let's get coding. First of all, what I'm going to do is make a new directory for this. For this, you'll need Go installed if you don't have it already. If you don't have it already, then probably now is not the time to go and install it. But maybe wait till the JS part and then you can do that. But if you do have Go installed, then make a new directory in your Go path. Mine is, if you're anything like me, it's at the default path of the Go folder in my home directory. So I'm just going to create a new directory. And I'm just going to open that up in my favorite editor. So here we go. Whoosh, here it is. Cool. And the first thing we need to do is I'm going to move this. Move it over here. I'm going to make this all a little bit bigger so you all can see. A little bit bigger. Let's not get crazy now. Go mod init. Let's just create a new Go module. And then after we've done that, what we're going to need to do is get the DRAND dependency using GoGet. GoGet github.com/DRAND. All right, so this is actually the whole of DRAND, but it has the client in it as well. What we need to do next is create a main.go file here. And once we've done that, we'll type package main at the top because that's what you need. We're going to import this DRAND dependency that we just installed. So that's what I just typed here. But we're actually going to import the client, which is at client, and that is the main client. But we're mostly going to be using the HTTP client. There's multiple different clients. It works over gRPC, and as I said earlier, libp2p. We're going to use HTTP mostly today. These commas shouldn't be there. All right. So next up, if you're following us along, we're going to have a constant. We're going to have our chain hash, and I've got my handy notes of the chain hash. All right, so chain hash, let me explain about chain hash. The chain hash uniquely identifies the randomness chain. So it's a hash of the public key, the genesis time, and the period that I was talking about. And what it does is we pass it to the client, and the client will actually ask for the chain info, and then use that hash or hash that chain info and compare it against the hash that we give it. And that allows the client to verify that it's talking to the correct randomness chain that we expect to be talking to. So it's really useful. And that the information that it gets, it will also get the public key, and it can use that to verify the beacons that are emitted from DRAND. Next up, we need some URLs of HTTP endpoints that our HTTP client is going to contact. Today, we're going to use just 3 URLs of League of Entropy. Protocol Labs are part of League of Entropy, and we have a testnet running at the moment with 3 endpoints in various different regions. So we need car. I'm just going to have URLs, and that's a slice of string for now. And I have those URLs written here. Here we go. So these are the URLs that our HTTP client is going to connect to. There's 3 of them. There's one in the US, there's one in the EU, and there's one in Singapore, I think. Cool. Right, once we've got those URLs, all right, let's start actually, let's try and instantiate a client. So we need a main function. And what first thing we're going to do is convert that chain hash that we've got as a string into a slice of bytes. The chain hash is actually hex encoded, so we just need to use hex.decode string. We're going to decode that chain hash. There we go. So my editor will have imported encoding/hex for me, which is super useful. Decode string, and then we're going to instantiate our client. And for this, we're going to use client.wrap. It takes an array of clients and then a bunch of options. We're going to use the http.forURLs helper function, and that takes like an array of URLs and creates a number of clients or as many clients as the URLs you've passed it. So I'm going to pass it those URLs, I'm going to pass it that chain hash, and then I'm also going to use with chain hash. Okay, now let me explain this just a little bit more. So what client.wrap does is it creates a single DRAND client from a set of concrete transport specific clients. And what it does is it adds failover, validation, and caching. And so this array of or slice of clients that we pass it in here can be of the same type. Like in this instance, we've got multiple HTTP clients, but there could be different types of clients. Like there could be gRPC clients, or there could be pubsub client, the P2P pubsub clients. And the idea being that if one doesn't respond, then it will fail over to a different one. But also it periodically speed test these clients, so it will ask the fastest client each time for the information. So if I'm actually, my server that I'm or wherever I'm running this is kind of in the US, and it's likely to be using this endpoint most of the time, but it will test these other ones periodically to ensure that they are not faster. So so that's what client.wrap does. That's what it's doing. With chain hash, so this is passing in that chain hash that we had up there. We can, if we wanted to, we could use insecurely. I don't recommend you use this unless you're in development, because it disables this check that the client has to ensure that it's talking to the correct randomness chain. So we're not going to do that today. So we need the chain hash. The idea is like I either pass the chain hash or all of the chain information, and under normal circumstances, and it's easier to have the chain hash than it is to have a kind of file or some sort of store of all of that chain information. All right, so once we've got our client and we've instantiated it, then we can just use the info endpoint to grab hold of the chain information context. So we're just going to use the background context. We're going to assign that to info. We're going to ignore errors in all of this and hope that everything works first time. So hopefully that'll go okay for me. And then we're just going to print out a bunch of all of this chain information that's interesting. So we're going to print out the public key. Plus B. There we go. Info.public key. We're going to print out, hang on, we need a few of these. Genesis, we're going to print out the genesis time, the period, and the chain hash. So genesis time, as I said, the genesis time is the time at which the chain actually started. And that is, so that's expressed in seconds. And so all I'm going to do is convert this into a time, so that when it gets printed out, it's going to print out nicely for us. Period, as I said, is the time between beacons. This comes back as a duration, so we can just print this out and it will come out nicely, nice human readable. And then chain hash, we're just going to print this out because we should be able to compare it with the chain hash we got up here, and they should be the same. So chain hash, when it comes back to us, is just a slice of bytes, and we're just going to encode it to a string in hex. Info.hash. Okay, so if I save that stuff, then it will have imported context, format, and time. I've got rid of all of the red stuff. This is, why is it not in my Go mod file? Oh. Yes, we have. Okay, so in theory, I should just be able to run this now. Go run. Hey. Okay, great. So we can see here that we've got the public key. We've got the genesis time. This was 25th of May. Yes, 25th of May. And the period for the test net is every 25 seconds. So every 25 seconds, we'll get a new beacon generated. The chain hash 84B22 is exactly what we expected. So everything is working correctly. All right, that's fun. But there's no randomness here. This is just information. Let's get some randomness. What we can do is use client.get. That takes a context like all of the functions that in the client. And what we're going to do, the second parameter is the round that we want. Rounds start at 1. If you specify 0, then you'll get the latest round. So you don't need to know what the latest round is. You can just say, get me the latest one, and it will get you that. So I'm going to assign that result to a variable. I'm going to ignore the error again. And then we're going to print out that randomness. We're going to print out the round number. That is, here we go, latest dot round function, and we're going to print out the actual randomness that we received as well, and we're going to encode. This is again just a slice of bytes, so we're just going to use hex.encode string again to make this reasonably readable. Okay, so that's how you get randomness. So how you get the latest random value from drand. So if I run this, here we go. So the latest round, we're on round 175,581, and the randomness is all of these bits and bytes there. Cool. All right. So how do I get a specific round? Well, it's kind of obvious. We can get an old round by just specifying the round number in the call to get. So if I get 1, 2, 3, 4, 5, which we have done already, and we'll print that one out. Here we go. Old round. Save that, run it. We should now see the latest round has incremented by a couple. It was more than 25 seconds since I last run this. And the old round 1, 2, 3, 4, 5 has this value of randomness. So, so hooray, all right, it works. That's how you consume randomness. Now, that's kind of interesting, but what's even more interesting is getting a live feed of randomness as it occurs. So let's do that. All right, so we can use watch, because the client has a watch function, and we can use that in a for range loop. So I can use for rand equals range c.watch. That's cool. Context.background. There we are. So every time a new randomness value is generated, it will be assigned to that variable there, and I'm going to print it out just like I did for these other ones. new round. And this is, I called this rand here, rand. Cool. So then we've got, and then what I'm going to do is I'm just going to put, done when we're done. Okay. So now I should be able to run this and we should get, I'm not sure what that is, but here we go, new round. So 586 is this round, 587 just got generated. And so when I watch, I should get the current round straight away. And then when the next round is emitted, then I should get that round. And so in 25 seconds, because we know the period between rounds is 25 seconds, I should get a new round appearing here. You should note that watch is kind of best effort. There's the possibility that it will, the channel that it returns will close. And so if you really care about continuing to watch, you should reopen that watch if it happens to close. But in an ideal world, that will just continue to watch for new randomness and output it as it happens. So here we go. We've got 587. Not sure what these are, but I'm going to ignore them for now. 588, 589. That's cool. And so if you'll notice, we never get to done because watch never closes. We've not finished it. So typically in Go, you'll use context to cancel things. So we can cancel our watch when we don't want to do it anymore by using a, let's just use a timeout. Context.with timeout. So what we'll do is after say 30 seconds, we'll stop watching. Context.background, we use that as the parent, and then we can use time dot second times, yes, 30 seconds. I said 30 seconds, didn't I? Okay, cool. So, and then instead of using the background context, we use this new context that we've got. And then so basically we should see after 30 seconds, we should see done printed. And so we get the current round, the latest round. We should see another round because we've got 30 seconds to work with. We might, if we were really quick, we might not have been quick enough, but we might see another round or we might not. Either way, that's how you cancel a watch. If you just bear with me a few moments, you should see this cancel and then, there we go, done, will be printed. All right, cool. That's the Go client, fun times. Let's do it with the JavaScript client. Okay, so this is going to be fun. Possibly more fun. For this, you need an index.html file. And in that file, just before I start, we have docs for JS client as well. They are, like I said, in a developer section under JS. It's written using ES modules, so it's all fun times new stuff that works in Dino and Node and on the web. So we're going to just use a HTML file for the purposes of this. It's HTML. Whoa. No. Okay, so that just tells it that it's a HTML file. We need a script tag with type equal to module. And then from there, we need to import our client. We import client and the HTTP client, just like we did in Go. And that comes from, well, any CDN you want, really. It's on JS Deliver, so it's as good a place as any, I guess, for getting it. So this works. This is cool. And we need that chain hash again. So I'm just going to steal it from over here. Some of this syntax is pleasingly similar. Chain hash. We also need the URLs. Let's grab the URLs. Let's put them in here. That's a constant as well in JavaScript. This is just an array. There we go. There we go. we go. URLs. We've got some URLs. Got that chain hash. And then what do we need? We need a main function. So I'm going to make an main, and then that doesn't get called for us automatically, so I'm just going to call it there. But in this main function, we're going to instantiate the client just like we did in Go, and we use await client dot. We're going to use wrap again. So this is you'll notice that the API is very similar with capitals in different places for we've capital lovers in Go on at the start of the words. So http dot for URLs. There we go. We're going to use our URLs. We're going to use that chain hash, and we're going to pass in that chain hash as well to the client. There we go. Okay, so I'm not going to get the info because it's a similar thing. You can call .info on the client. So let's just get the latest one again. Latest equals await on c.get, and we don't need to pass any parameters. You can pass it 0 here, but it's JavaScript, so it doesn't matter. It's faulty. So it will just get the latest if you don't pass it a particular round number. We're going to log out console.log. We're going to log out that latest round. Oh man, my typing's getting worse as it goes on, isn't it? Okay, latest.round. Log out that latest round, and we're going to log out the randomness as well. There we go. And in theory, I should be able to just run this. I'm going to go open index. There we go, open it up, and I should see a blank screen as I am expecting, but in the console, I should see logged out the latest round, 175602. I should see the latest randomness, so that's all working in JavaScript as well. Hooray, with pleasingly similar syntax. We can get the old one as well. Let's do that, it's fun. Old. 1, 2, 3, 4, 5. Let's do it. Got an old round, 1, 2, 3, 4, 5. And so in theory, so this old round 735F614, if we go back over here and have a look at our go up at 735F614. Okay, they're getting the same information from the same chain. So so stuff is working. We can watch in JavaScript as well. I'm not sure if I said, but watch in the HTTP for the HTTP clients, it's actually not a real stream. So for the gRPC clients, it's an actual stream. It's an open connection that remains open. But for HTTP, it's actually the HTTP client calculates when the next round is meant to be available, and then makes a HTTP request when it's available, and then yields it essentially. All right, so we can use, so in a similar way, we can use for await of c.watch. Okay, so in JS, when you watch, it returns an async iterable, and then we can use that in a for await loop and to do something very similar to what was happening in Go. We're going to log that out. We've got our new round. It happens every so often. New round, new randomness, rand. Okay, let's have a look. There we go. So that's the current rounds, and the next round has just come through. It all works, hooray! What's kind of cool is that the rounds that in JS, when the rounds come through and the client verifies them, that's done using the code that that is written in the Go client. It uses WASM, it's compiled to WASM, and then and it's downloaded and verified using the WASM in the browser, so it's nice and fast. A previous iteration of the client was doing that verification in around a second. Now it does it in between 80 and 100 milliseconds. So that's much better than it was. Hooray. And cool, that's the JS client. All right. Now, the most fun bit. This is getting more fun as time goes on. All right, check this. So we've done some getting randomness using JS, but let's get some randomness and use it in a web application. How do we even use this? All right, so this is our web application. This is our dice roller. It's chosen by a fair dice roll. It's guaranteed to be random. When we roll, it sort of does a roll for about 5 seconds and ends up on 4. When we roll again, it does the same thing. So we need to fix this because it's just a 4 roller. As David showed in his slides, if you're familiar with the XKCD, then you will be laughing at this already. Cool, so let's fix this up. Let's go to a different project. Here we go. The dice roller, here we are. Now I'm just going to start serving this. Right, let's look here. Okay, so what is this? So this is the code. This is the HTML code behind the page that I just showed you. There's some style that you don't need to worry about, but it's essentially a div with the dice value on it. There's a button that says roll. That's cool. And then there's this little script, which we're going to start with main.js. And all this script does is obviously it gets hold of that dice element, gets hold of that roll button, and then it adds an event listener, a click event listener on that button. And it disables the button, stops people from pressing the button after they've pressed it once. It starts the roll. So we're not going to look at this, but this magicness starts the dice rolling. So all it does is it takes the dice element and it puts random numbers in the dice, so it looks like it's rolling whilst we get our random value. And whilst that's rolling, we set a timeout for 5 seconds, and then we stop that roll with the value 4. So that's what's happening every time I was pressing the button just then, and then undisabling the button. So we're going to fix this so that it works in using Drand.js, and so for that, we need those. I need the stuff I had up before. Let's grab that. So, whoa. So I need this chain hash and the URLs that I was using. I'm just going to add them in at the top here. There we go. Okay, that doesn't matter. And then I'm going to import and instantiate the client as I was previously. I just need that import again from here. Import it and client. Here we go. Here's the client. Oh, yeah, not there. We're going to put it in here, instantiate it when we call main. There we go. So now we've got a client that we can use. Oh, we need to make this an async function. And so instead of this stuff, we're going to keep that remove attribute. We're not going to stop the dice rolling at the number 4. So we're just going to remove that bit. But after we set the dice rolling, what we're going to do is we're going to figure out what the next round number is going to be. So we can do that by next round number equals, we can use round at. So this is a client function. This is a function on the client that's available in JS and in Go, but you give it a time and it gives you a round number back. So for right now, the round is going to calculate what the round number is. What is the randomness value that has, what is the round number of the randomness value that has been generated? And we're going to +1 onto that because we actually want the next round that hasn't yet been generated. And then what we can do is we can say rand equals, get that next round. And so the interesting thing that happens here is that when you ask the HTTP endpoints for the next round, like you can't ask for future rounds, but you can ask for the next one. It will block until that round's available. So it won't return until that round has been generated. So I can await on this get next round. And then once it comes in, I need to convert that randomness value, which is a big long string of hex encoded data, into a number for our dice, right? So I'm going to say num equals, we're going to use big ints because that's fun, right? We're going to say that it's some sort of hex here, randomness. And then what we're going to do is we're going to mod that by 20 because we've got a 20-sided dice. So we want a value that is in that range of 0 to 20, right? Or 1 to 20, essentially. But this will give us in a range of like 0 to 19. So we're going to add 1 to that. And so we need to, if I want to use mod and plus, then I have to tell JavaScript that these are big numbers, and I can put n after them for that. And then I'm going to, once I've done that, once I've converted the randomness from drand into a number that can be used in my dice, I'm just going to call toString on it with base 10, and then I can use my current roll.stop, pass it this number instead of 4, and that should, in theory, work. Although I haven't demoed this, so we'll see if it actually does work or not. We did a run through and this didn't occur. So I started this up on localhost 8000, I believe. So it should be here. If there's no errors in the wait, yes, that's true. Okay, here we go. So, oh yeah, okay. Async. I think that's okay. Let's try again. Get out of the way. Okay, that looked like it might have worked. So I should be able to now roll a dice, and it should. Oh, so yes, here we go. 6. Hooray! All right. That is super rad, and I should be able to. There's always a chance that it lands on 4, and then I'm like, oh no. So rolling it again. So the interesting thing is it can take up to 25 seconds to roll the dice now. So that's an interesting one. So we're on 9, but now we have unbiasable, verifiable randomness driving our dice. No one can interfere with our dice rolling, and you can use this when you need to roll a dice for some board game or something. So super simplified use case, but you get the idea, right? Okay, hooray! All right, so how much time have we got left? Okay, not very long at all.
If we go over a couple minutes, that's all right.
Okay, cool. In which case, I'm just going to the next bit is libp2p pubsub and getting randomness off the libp2p pubsub network. I'm going to explain why you might want to do that, and then I'll just I'll show you. I got a pre-canned already done. I won't have to actually code it in front of your eyes thing that I can show you. So I'll do that, and then if you want to. I'll explain it, and if you want to go and use it, then you're quite welcome. But that will hopefully save a little bit of time. Cool. Okay, so the next bit is kind of watching for randomness over libp2p pubsub, and so using libp2p pubsub as a transport is a means of mitigating risk. If you rely on receiving the randomness that drand generates, then using different transports with the client gives you alternative means of getting hold of that randomness. And so and that might be because it's more reliable, but it might also be a little bit faster if you use different transports. So for example, like you might find whilst your drand client is running, an ISP blocks HTTP traffic to a particular URL. So maybe a different transport can then service your requests. Maybe, I don't know, maybe DNS goes down or is like sabotaged and pointed to like a rogue drand machine. I mean, that's kind of okay, because if you get pointed at someone and they're generating random values, then it won't be able to, because the client verifies the random values and they'll be thrown away essentially. But other transports will be able to satisfy the requirements. So that's good. And I think David already said, but we've observed that actually receiving randomness over libp2p pubsub is faster than over HTTP in China due to the overhead that the firewall adds. So that's fun. So anyway, let's get on with it. Let me show you this. So recent one. Here we go. So I got this all done. This is similar to what you saw already in the Go client. This bit is new. So previously we had. Let me show you just here. Well, I've basically deleted this stuff. Now I've deleted that stuff and added this stuff. I've also added this listening address. So this is a listening address that libp2p can listen on. But the most important thing is these relay addresses. So these are libp2p nodes that the League of Entropy, that Protocol Labs are running, that you can connect to with libp2p pubsub and listen for randomness. Cool. So what I've done, why I haven't deleted this, because what I'm trying to do is prove that this works entirely over pubsub. And so we're going to create a client, or we create a new client. We create one client and then we create another one. We create this new client, and that has no ability to talk over any other transport other than pubsub. And so the reason why this is a little bit weird is because with pubsub, you can only receive new randomness. Like there's no way to ask the pubsub network for the chain info. There's no way to ask for that. So what we're doing is we're getting hold of the chain information from the HTTP client first. And instead of passing the chain hash, we're going to pass the chain info to the client, which means that it doesn't need to then go and get that chain info so that it can verify that it's talking to the correct chain. And so like verifying pubsub messages or randomness beacons that come over pubsub is extra important, because over pubsub, over peer-to-peer pubsub, the randomness beacons can come from anyone. Like they're not coming direct from DRAND servers or DRAND relays. So that's kind of good. So here we go. So we've done a little bit of admin here. There's a libp2p package in DRAND, which allows you to, which has some helper functions for constructing a host, loading public keys and private keys, sorry, or creating them. But essentially the interesting bit is, so we've got G client, I've called it G client. So we're importing client from libp2p. It's G is for gossip, because that's the flavor of pubsub that we've got implemented here and we're using. So we create a new client, we're just using pubsub. And then we're watching for randomness. Yeah, so as I said before, the interesting bit about this pubsub client is that it has no facility to get the info. It also you can't ask it for any round. Like you can't say, give me round number 1, because it can only give you back stuff that it receives, it's seen before, has been published to it. So you can ask it, so you can call client.get for any round that you've seen before, because it might be in the cache, but as it is here, you can only watch for stuff essentially. But typically what you do is you'd add this pubsub client in combination with a HTTP client. So you could go and get the info and it will fail over to HTTP or vice versa. If maybe, the randomness beacon doesn't come through pubsub in time, so it will come from HTTP, it will work it out for you essentially. Anyway, so that's the explanation of everything that happened here. It takes a lot longer if I just type it out as well. In theory, I should just be able to run this main.go. And this client, which operates only over libp2p pubsub, should then start receiving. So we shouldn't worry too much about one of these endpoint temporary. Yeah, this is fine, because what it's trying to do is it's the optimizing client that we're using is speed testing all the clients it gets, and it's speed testing the pubsub client, which, as I just told you, we can't get it can't get any old random value. And for the speed test, it tries to get the first round from the chain. And we haven't seen that over pubsub yet. Okay, so what happened here? Okay, so we've got a new round. Oh, we still got our context with timeout. So it timed out after 30 seconds, but this worked. This got the round 175645 over a libtcp pubsub exclusively. There was no other way for it to get that round from anywhere else. So so I'm super happy, and that is essentially all I have to tell you about the Drand client. And I hope you enjoyed it as much as I did. I can take your questions now if we have any time, if anyone wants to say.
That was amazing.
Great stuff. I have questions, many actually. So first, how is the period? I guess it is network based because decentralized time or getting a trustable time source is already a big problem. So how does this period come? So if you get a timestamp, you get an absolute time. How do you come to that, and what is the variation in that?
Yeah, I can take that one. So that is because the randomness comes from a small number of nodes, which are the Drand nodes, and they are all synchronized, like just using standard NTP. And so the nodes themselves will generate a partial signature at every epoch, and so that epoch gets defined when there is a Drand ceremony to set up the network. And so if it's 30 seconds, then they all agree that at every 30 seconds, they generate a partial signature. And so when they all generate a partial signature and that partial signatures get assembled, then that randomness gets broadcasted. But so the way to think about it is you have a small core of protected nodes that are with their clocks synchronized, because it is simpler to have a small group synchronized than try to synchronize the whole world, right? And so you are able to rely on that clock time, but when it gets to the client, that timestamp that you see on the client, you can measure the discrepancy between the previous round and the what you just received. And so you receive a round, you measure from here, I should be receiving another round in 30 seconds. And if there is some delay there when you receive it, you can either give that to the latency between the Drand node network, distribution network, the client, or yeah, might be some other issue in the middle. But yeah, I hope I answered your question. I might not explain other parts.
But let me ask a high level question. So it is a permission network.
Yeah, permission network.
With a setup ceremony. If there is some leak, it's unsecure in the setup ceremony.
Yeah, if the enough nodes, well, let's define insecure. So in order for someone to gain a privilege, such as being able to predict the future, they would have to compromise enough nodes, and that enough is n equals the threshold, right? So if the threshold is 7 of a network of 10, then you have to compromise 7.
Yeah, but with a small permission network, they could collude to do.
It's different operators with different interests, with different geographic locations, under different restrictions.
Yeah, well, but I cannot verify because it's a permission network.
Well, you are verifying that you trust. When you accept the League of Entropy, you are trusting the partners, right?
Okay. Yeah. Okay, but it's interesting because it's a very hard problem, and usually the problem is with this kind of all kinds of synchronization is the communication overhead, and this is why proof of work is so strong, because it solves the communication overhead, because you don't have to communicate to come to consensus.
Yeah.
So it scales better in the number of nodes. Of course, it's energy intensive. You said that verifiable delay functions are out 2 or 3 years. I'm very interested in that because it's kind of like a proof of work, which is not parallelizable, but it's serialized proof of work, so you cannot compete. So it would probably solve the energy problem. Why do you think it's 2 or 5 years out? What's so hard on the problem?
That's a great question. And so I'm actually not a VDF researcher. I got that information from the team that is doing research on VDFs, and that's what they told me.
Yeah. Okay. Thank you. Great initiative, great project. I love it.
Yeah, awesome. Thank you.
One other question, because
bring it on.
If you have reliable decentralized randomness, that would solve many problems in consensus-based systems. And what I don't understand, how can it solve the problem if you have a separate chain that, let's say they have they have solved the Sybil problem, they have a permission set of verifiers, and they want to use randomness to, let's say, select the leader of the next block. Then they would still have to rely on an external source for the randomness with DRAND. And this is, I think, a problem within any kind of a consensus system that is closed.
Wait, I'm not sure if I followed. So you're saying that like even after using DRAND, they still need to rely in an external source, or like DRAND being the external source in the first place?
Yeah, look at any blockchain like Ethereum or whatever. They cannot rely on any external information to come to their consensus, because external information is unreliable in the sense that you might not be able to connect to the network. The DNS might be spoofed or whatever.
Yeah. Yeah. And so, yeah, you're right. And so like one of the attack vectors is that like, if the network is down, if there is an outage, like there are, depending on the construction of the blockchain that is using the randomness, it could either halt or could either lead through some like uncertain behavior. And so the way that we approach this, like Filecoin actually has in its protocol ways to be able to make progress, even if there is a DRAND outage. But then the premise is that like DRAND, by being a distributed network run by multiple parties, where you only need a threshold of parties for the network to have liveness. And because these parties are running their DRAND node in different infrastructure, right? So like we have people like running in private clouds, in like public clouds, in other data centers. Like there's like all sorts of diversity in terms of like geographic location, connectivity, infrastructure, hardware. Like there's like so much diversity that like in order for an outage to be complete, like a complete blackout, is essentially you are attacking the whole internet, right? Because now you have to take down all of these data centers at the same time. You have to like compromise these organizations all at the same time, and so like it just like increases the cost of the attack very high, right? And so
but I guess that separate chains that want to rely on some kind of distributed or decentralized randomness could integrate a DRAND into their project directly. I think that would be and
and so the way that like
how many can be in the set of you said it's a small core. How big can be the set of nodes that come to consensus about the randomness?
It can be as big as we want. Of course, like when we reach to a big number, then like if we were to have 1,000 nodes or like 1 million nodes to be part of it, then like we have another scalability problem within the small group. But right now we are already over 13 nodes, and like we seek to increase that number. And so the more nodes we add, the more secure the network is. But also as we increase the number of nodes, we also increase the threshold. We have a way to kind of like project what is the best threshold for a network size n. And typically it's like anything between more than half and below 3/4 of the network. So that like you have a network that is both secure, that has like a very high cost to attack, but also that has a very high probability of having liveness. Like if you have like some kind of like some safe assumptions, such as if you assume that like between 10 to 20% of the network could have an outage at any point in time, because all kinds of like services have outages anyway. And then if you take into account, and then if there is an attacker trying to compromise nodes, like how many nodes do you have left that could be the threshold so that the network has liveness. And then the other thing is, in the case of events that like someone compromises the network for some reason, right? Like let's say that there is like a very rich malicious actor that has a lot of friends in a lot of companies from different countries, from different industry sectors, right? And as able, like there is always a way, like, and like if the network halts for that reason, there is always a way to see which nodes stopped generating the partial signatures and do a reshare or even a new ceremony to kick those nodes out that are malicious, that are behaving incorrectly. And so there's like it's kind of like better safe than sorry. Make sure that like have a network as diverse as possible and have like a very like tight monitoring. But like in the case of a potential attack, have like the equivalent to fraud detection, like monitor like some weird behavior and like exclude the weird behaving node out of the network.
So okay, so what is the precision of the clock that you get basically? So are you off by if I connect to one of the nodes and get the randomness beacon? Am I do I have a margin of error of a second, 2 seconds, 5 seconds, milliseconds?
I mean from generation to actually receiving it?
I don't know how the time is fixed to anything because there is no absolute time in the sense of
yeah. So like from our monitoring, so like we have this thing that we call the network observatory, where we have just multiple probes in multiple geographic regions that are just like receiving the randomness and see how fast they get the randomness from the multiple distribution network endpoints. And so like it went between like 500 milliseconds and 1.2 seconds, right? So the slowest would be receiving the randomness like 1.2 seconds after. But like if you think about it, because the randomness gets generated every 30 seconds, it means that like every node, if every node gets the latest number between 500 milliseconds and 1.2 seconds, everyone still has like 29 seconds, like or close to 29 seconds with a value already cached in their node, right? And so it gives you like a lot of time for everyone to receive the randomness and ensure that everyone has received the randomness before the next round is produced.
Who sets that? Basically, which entity in the network sets the final time of a randomness beacon? Some leader node, or who defines that time?
It's not like so. Think that like we are all independent in the Zoom, right? And so every 30 seconds, I will generate a partial signature, like. And then when there is one of us, and then I'll send a copy to each one of you, right? Like when one of us has enough pieces and enough is equal to threshold,
he says,
smashes them together and pushes to the distribution network. And that's like when others receive it.
And he writes the time.
No,
or
I'm not sure. Maybe I don't understand just the question.
Yeah, well, there is a time associated with the randomness beacon, and you say, okay, I collect all the signatures. If I'm a node, I have all the signatures that are enough to come to a decision.
Yeah.
And then I write in the time and send it out, or where's the time fixed?
I see. I got you now. Like you are asking if the time is the time that is like when the partial signature is created or when the partial signatures, plural, are assembled. That's a good question. I don't have it fresh in my memory. Hector or Alan, do you actually know right now on top of your head? Otherwise, like we can always check it.
No, I don't think there's like a timestamp that gets saved anywhere for when something is ready. There is a time that when it should be, when it's meant to be generated, right? And then there is like the time between that and the actual thing being ready and available to the network for people to, and that's just a small amount of time.
Yeah. And because like there is a period, right? And so independent of like wherever your clock is synchronized to, like you can always estimate, because given that the epoch is fixed, like 30 seconds, well, in planetary is 30 seconds for everyone. When we have interplanetary randomness, that will be different. But like as soon as I start receiving randomness, I can then predict when I should be receiving the next one, right? And so this is where like we see the discrepancies. And yeah, well, but I'm also happy to follow more on this question, because I see that you asked a couple of times, so maybe there's something more that we can just demonstrate.
Okay.
If you can ping us on the Slack on the HackFS.
Yeah. Okay. Thanks.
Okay, so something about DDFs, but I keep mentioning Juan's talk. Yeah, like there was a question brought up in here in chat, just like for the record. yes, when you are using cryptographic code, definitely make sure that it gets audited. Like you should not just download things from the internet and just trust it, because if you download some client library that was manipulated by someone, the best that we can do is make the code available so that you can like check it out and like audit it. And then we can hash it. And like when we publish it to a CDN, we can provide the hash so that when you download the code, your browser can verify the integrity that the code that you downloaded is actually the one that reproduced. And this is like one of the techniques used in like the web/JS world. For the Go world, we have signed commits. So you can always like git clone and like build your own or just like import the library and then like build it yourself to make sure that like you have the right thing. Definitely always be extra careful when importing anything that has to do some cryptographic verification, because if there is someone that is able to mess with that code, then could potentially be fooling you.
Yeah, you can do the same thing with JS as well, right? For a lot of applications, you bundle up that with your application code. So yeah, like it doesn't have to come from a CDN, but
yeah, that's also true.
Convenient.
All right, I don't see more questions or people. And
I added one more if you want to get that.
Is there a way for an attacker to affect liveness if it belongs to round N and attackers make sure that the CLI or randomness consumer may not be able to consume? So you are saying, or rather than attacking the source, attack the destination. So it eclipse the receiving node. And so if you have the power to like, well, did I get the question right? I hope. Yeah. So if you have the power to eclipse entirely, let's say like you have the power to like completely shut down the internet of my home, like you will effectively have the power to like isolate me from the rest of the network. That said, we are making it extremely hard, because let's say that I am in a network that has blocked Cloudflare, I can still go to CloudFront. Or I am in a network just blocked DNS as a whole, I can still use peer-to-peer pubsub that doesn't rely on DNS to fetch the randomness, right? And so we have multiple transports to deliver the randomness. And so it is incredibly hard. Of course, if someone cuts the cable that offers internet to the location where your machine is, then well, you have other troubles as well. Like it's not just the RAN that goes off, it's the entire internet. I hope that I answered your question.
Yeah, I think that probably covers it. It looks like Will has actually been in the YouTube chat answering a bunch of questions, so that's great. I think he covered most of them. So we could probably wrap up there if there are no last minute questions. If anybody's still unsure about things or has additional insights that they're looking for, you can definitely connect with David and Alan in the Slack. They'll be available in probably all of the channels. Thank you both for presenting. Alan, when you went through, I could feel your excitement at the correct results. That's always nice when it works the first time. So congrats on that. And thank you for giving an excellent workshop. And this is perfect because we have it recorded and it'll go directly onto the ETHGlobal YouTube, like I mentioned at the start. I think we can probably wrap it up there, Andrew. We'll see everybody in Slack, and there are office hours tomorrow, and as well the hack feedback session on Friday. Thank you.
Thank you. Thank you so much for hosting this. It's great.
Yeah, thank you.